in machine learning, what it means, how to quantify it, what the implications of not having data privacy, what are the privacy risks and the consequences. So it's going to be rather a comprehensive introduction. I won't go very deep into the technical details, so it's meant to be an introduction. So the privacy regulations and many guidelines in AI security and privacy, they all call for an analysis of privacy risks when you touch sensitive data, including the technologies such as machine learning, right? Most of the focus, however, is on access control. Like who has access to sensitive data, right? And confidentiality. Whether sensitive information could be reached by someone who must not have access to that, some unauthorized entity. Who the data should be shared with, and so on and so forth. But that's not all the privacy risk, right? So even if I have access control in place, I'll make it clear to you that it does not prevent all the privacy risks, right? So the privacy risks are more subtle than that. To define what the privacy risks are, I distinguish two different types of privacy risks. One, which I call the direct information leakage, and then the other one is the indirect information leakage. So for the case of direct information leakage or direct privacy risk, for example, in the context of machine learning, you can imagine that there is some entity, some computer that have access to the training data during training, or has access to the inference data, right? So when users send queries to get predictions on their data, then that entity has access, direct access to the user's data, and if the data is sensitive and that entity is not trusted, then their privacy is in danger, right? So this is obvious. This is where access control, confidentiality, and other protection mechanisms could be helpful, right? So you don't want unauthorized entities to gain access to where the training data is stored. Also, you don't want an unauthorized entity or someone that you don't trust to even do the training, right? So then that's the access control as a protection mechanism. Also, there's confidentiality measures that you might have. For example, you want the training to happen and be performed on encrypted data, right? So even the computer that is running an algorithm on the data should not be able to see the data, do some sort of a blind computation. Okay, but that's not all the risk, and that's not all the protection mechanisms that we need. There is this indirect information leakage, something which is more unintentional and something which is harder to, and more subtle to evaluate and protect against. The machine learning model, and therefore the predictions that come out of the machine learning model, are functions of the training data, right? So information theoretically, there is something about the training data in the model and in the predictions that the model generates. And you can imagine that there would be some adversary who would look at the model or the predictions from the model and try to reconstruct information about the training data, right? So that's what I call the indirect information leakage. The adversary does not have access to the data, has no idea what the training data is, however has access to the model or the predictions from the model. And here, there's no way that you can put any access control to prevent an adversary to do these inference attacks if that information leakage happens, right? Because the adversary here is actually the user of a system, right? So you train a machine learning model, you want somebody to run queries and get predictions, right? So, and if the predictions leak something about the training data, there's no access control that can prevent that leakage. So what we need to do is to evaluate how much those models actually contain sensitive information about the data and how we can systematically prevent them during the training to even memorize that information. Right? That's the general idea. So is this risk real? Yes, that is real. We can actually run inference attacks against existing machine learning as a service platform by all these cloud service providers, and tell with very high accuracy whether certain data points have been used for training a model, right? So you have a bunch of data, you're developing some mobile app, or you want to use machine learning for your systems. And what happens is that you upload your data to the cloud, you ask them to train a model on it, and then you have API access to the model. You just send black box queries, right? And so do your users who are going to use your model, right? So they are going to have indirect access to your model. And these simple API calls doing predictions on the data would leak information about their data. If an adversary has access to the model itself, like for example in the case of GPT-2, which was released, and many other large models which are trained on potentially sensitive data, the adversary can not only just query the model and look at the predictions, but also look at the model parameters and all the details, and actually can reconstruct some information about the data in this the context of language models. It can produce sentences and documents that were actually used for training the model, which you can imagine that could be very sensitive, right? So the attacks are possible. The attacks are happening, right? So there is information which is memorized by the models and could be extracted out of the models. If you have heard of federated learning, where multiple parties get together and they try to train a model together without sharing their data with each other for privacy reasons, then you can show that the communication that they have, the information that they exchange with each other throughout the federated learning protocol leaks a lot of information about their local data. Again, they're not sharing their data, nobody sees their data, nobody accesses their data, but the information, which is the locally trained models on their data, when shared, leak information about their local models. Right? So, which defeats the purpose of federated learning. There's a lot of hype around federated learning as being the another privacy-enhancing technology, which it is not. So, the conclusion from all this, possibilities of attacks against existing technologies, existing models and algorithms, is that if we are training models on personal data, models themselves are personal data, right? So they have to be treated as a sensitive piece of information, and as sensitive as the original data is. And so what we need to do as computer scientists, what we want to do is to just not to showcase corner case or particular examples of possibilities of attacks, but also to evaluate leakage, evaluate privacy, evaluate security, put some numbers, and to be able to measure how much is the leakage, so that after modification, after we design a defense algorithm, we would be able to go and see how much we have improved on the metric that we have designed. So the metric also should be designed very carefully so that it actually reflects the true notion of privacy that we care about. So what do we care about here? Let's agree that what we care about is that we don't want the model, or you can replace model with anything, any piece of information, any aggregate information in a statistic. But in this case, we don't want the model to leak significant amount of information about individual data records in the training set. Right? So we care about individual privacy. Imagine that the data is partitioned into some records, right? So hospital records, documents by different users, and so on and so forth. And you don't want the model to leak a lot of information about every individual data record. So what does that mean? And this is very subtle and also very important to understand in order to appreciate the kind of mechanism that we want to use or algorithm to quantify privacy. So the model that you train does contain information about every individual data record in its training set, right? And that's how it learns some patterns that later on would be applicable on test data, right? So the information is learned from the training data, right? So what is it that we would call information leakage, and what is it that we call the useful information that the model has learned? So let's consider that you want to provide your data, contribute your data to a training set of a model which is going to be released later on, right? So what would you be concerned about? You would be concerned about the following. If without your data, including everybody else's data, if without your data, somebody looks at the model and you didn't contribute your data, the adversary learns something about you. He has learned it by just extrapolating whatever he learned about the population on you, right? So people have common features, their data also have some common features. There are some common patterns on the data, and the role of machine learning is to just learn those common patterns, right? So if I learn something on people that have this particular disease with these features and so on and so forth, then I would be able to apply it on some other people and make predictions on their data, even if their data was not in the training set. That's exactly the goal of machine learning, right? So you would not be concerned with that. You would be concerned if whatever the adversary learns about you when your data is in the training set is way more and different than whatever he learns about you when your data is not in the training set. Which means that he not only learned your contribution to the general patterns, but also he learns the specifics of your data, right? He didn't learn that, you know, smoking causes cancer, which is what we wanted to learn from the whole data. He learns that, you know, you had cancer. This is beyond what you want the machine learning model to learn, right? If your data was not there, he wouldn't have any way to know that you had cancer. But when your data is there, all of a sudden the chance of saying, oh, Alice has cancer increases significantly. And that's the information that you want to be leaked. So is that super clear, right? My estimation, inference of something sensitive about you will change significantly when your data is contributed to the data. That means that the algorithm is to be blamed for that leakage. Right? So how do we quantify it? Now that we have at least one definition for, a vague definition for what we mean by individual privacy and information leakage of an algorithm, let's see how we want to define it. We define it by designing a game. Okay? So I'm going to design a game. I'm going to create two parallel worlds. Assume a training set, and then a particular data record Z. And what we do is I just say, well, in one world, on that training set, the particular data set Z is a member of the training set, right? So Z contributed its data to the data set. And in the parallel world, the alternative world, the data is not there. Everything else is the same. All the other records in the training set are the same, except that his record is not there now. Okay? So then in these two parallel worlds, we train machine learning algorithm using the same algorithm, let's say a neural network with a particular architecture and so on and so forth. Of course, there could be some stochasticity and randomness in the training, but the algorithm is the same, right? So we train two models in parallel, right? And then we place, we get some hypothetical adversary, let's say someone who is capable of doing the best inference attacks. And we place this adversary in one of these worlds at random. So with 1/2 probability is there, with 1/2 probability is in the other one, and we ask the adversary whether he can tell in which world he is in. Right? He has all the information. He knows the training set, he knows Z, he knows the training algorithm, he knows everything. Now he gets two samples, right? One sample, right? He's in one world, he gets one model, he needs to now tell whether Z, he's in the world where Z is in the training set or not. So you admit that if he can tell the difference between these two worlds, he can tell because the algorithm leaked information about the presence of Z, right? There's no other information, the only difference is Z. You can repeat this experiment many times, let's say for a particular Z or for different Z, for different training data and so on and so forth, and overall you will see how much would the adversary be able to tell where he is in either of these two worlds correctly, right? So you put him in different worlds and then he has to guess and so on and so forth. So now basically we connected somehow the success of an adversary in that game with what we vaguely define as individual privacy. Okay? So that's the idea. That's why we went to and designed this game. So then the question is, okay, what is the algorithm, what's the technique that the adversary should use over there to perform this attack? Because it's true that we designed this with this hypothetical adversary, but eventually we want to go and quantify privacy risk, so we need to replace adversary with an algorithm. So what is that algorithm? So that class of algorithms are called membership inference attacks. Membership inference attack is an attack where, given a model and a given data points, the adversary tries to tell whether that data point was part of the training set of the model. Right? That's membership inference. So if the adversary succeeds in doing membership inference attack, means that he is able to tell the difference between the worlds where the data point is there or is not there, and therefore the model is leaking information about that particular data point under that setting. Again, if you repeat this for different data points and so on, then you get an overall estimation of privacy risk, which I'll get to. So these membership inference attacks are very canonical types of attacks. Right? So we just ask for one bit of information. Given a record, is it there or is it not there? So this kind of attack, it seems very simple. Again, it's a very, very hypothetical attack, right? So no one in the real world out there might care about running the exact membership inference attack because it requires knowing the data record, right? So it's mostly for quantifying the privacy risk. But it's the stepping stone of many other attacks, right? So I mentioned, for example, that language models, you can construct the sentences that were in the training set and so on. They use membership inference attack as an oracle. Right? I can just generate a sentence and say, okay, is this sentence possibly part of the training set or not? If the score is high, I would basically infer that, decide that actually this is a sentence from the training set. So it could be used for reconstruction attack, but here we just focus on its position in privacy auditing. And it has been over the last few years that this was designed for machine learning algorithms. It has been recognized by so many privacy and security regulations and guidelines and so on as basically as a tool to evaluate privacy risk, and also as a technique that actually reflects the risk, right? So if your model is susceptible to membership inference attacks, it means that it leaks a lot of information, right? So we need to be careful about that. So we had this game. We agreed that the success of adversary indicates information leakage about the model's training data. And we need to also go and construct such algorithms, right? So now our job is to go and construct the membership inference attacks. Before that, I want to make it a little bit more clear on, okay, let's assume that I run membership inference attack. What exactly is the kind of performance or measures that I get out of the attack, right? So if you give me one model and one data point, I run the attack and it tells me is member or is not member. So the attack could be right or wrong, right? But this is one model, one data point. I want to compute the privacy profile or information leakage profile of the whole algorithm. So how do I go from this one binary response to a metric for the whole model? What I can do is to design the game in the way that I want to evaluate privacy risk, right? So let's say you have a fixed data set. No matter what, you want to train a model on that fixed data set. Your question is, how much is the risk of this machine learning algorithm on these particular data points that are in this data set that you have, right? So then what you do is that you run the game by basically going over every individual data records in that set and then do the measurement, right? Sometimes you are not concerned about the particular data set. You just say that I have an algorithm the data could come from from a particular distribution, but I'm not fixed on a particular data set. So you just say, well, I randomize the training set construction as well. So what I do is that when you run the experiments for running the inference attack, you sample a data set, you pick a data point from inside or outside the set, you run membership inference attack. You pick another data set, you run the algorithm, you run the attack, and so on. So overall then you have many experiments of the game depending on what you care about, measuring the information leakage of the algorithm, or measuring the information leakage of a particular model which is trained on a particular data set. Anyway, then you get just a number of queries, and then the predictions from the attack as being member or non-member, member or non-member, and then the attack can make two types of errors, right? So if you query a member, it might mistakenly say that, oh, this is a non-member. Or it can make the other error, that is that you query a non-member and mistakenly says that this is a member, right? So these are the two kind of errors that it can make. False positive, something which is non-member, falsely tagged as member, or false negative, something which is member, falsely missed by the attacker. So then what we can do is just say, well, I have this false positive rate that I computed, which is the average false positive error of the attack over these repetitions of the experiment. I have the true positive rate for that. That gives me one point there in this plot, right? So that's a single attack. I have a single algorithm. I just repeatedly use it and gives me that attack. But maybe what you want to say is that, well, if I have an attack strategy, if you are an attacker, you might say, well, if you allow me to have higher false positive rates, maybe I can increase my true positive rate, right? That's all the trade-off that I have, right? So for example, you can just say, you can predict everything as member, right? If you predict everything as member, true positive rate is maximum, but false positive rate is also maximum, right? So the attacker basically, for every false positive rate that we allow the attacker to tolerate, he might have a different instance of an attack. Okay? That gives the attack profile. So for every false positive rate, I have a different true positive rate. If this plot is towards left, your left, and up, basically is that the privacy risk is higher, right? So for every false positive rate, the true positive rate increases, means that the privacy risk has increased, right? And the overall region under this would reflect the average privacy risk of an algorithm. So if this area covers the whole box, that's a maximum information leakage. It means that the adversary, even with very, very small false positive rate, would be able to tell who is member, who is non-member. Okay, it's not going to confuse any member and non-member. What we want to do is to, of course, design algorithms for membership inference attack, which are very accurate, right? So if you want to measure, how strong this building is, you want to go and get the tool that makes a very precise measurement of the strength of this building, right? You don't want to underestimate, overestimate it. And in our case, basically what we want is that we want to design stronger attacks so that we are not underestimating the risk of an algorithm. So we want a better attack strategy and a better attack strategy. And then this is where the research is on how to design attacks which are stronger and stronger in order to be able to measure leakage. So there is some unknown optimal attack strategy that we are unaware of, right? So everybody is pushing towards constructing that attack. We don't know what the attack is. And basically that is the one that reflects the true information leakage of a model, and there's this gap that we need to close, right? So you can come up with some basic techniques, and that basic technique might underestimate the risk, so you want to basically improve it. Right? Something that we need to be very careful about is that, as I said, the attack is, any attack will just give you a lower bound on the risk, right? So it's not that if a particular attack, a particular machine learning algorithm has low risk with respect to an attack means that the true underlying risk is also small. Maybe your attack is not as strong. So we cannot use this as a way to prove that we have a secure system or privacy preserving system, but it could be used to rule out the systems that are obviously leaking information. Right? So it could be used as an auditing technique. Then you would say, well, if this is the case, eventually I want to deploy. Okay, let's say we get an auditing algorithm. I know how to measure the privacy risk of my algorithms. Compare different algorithms with respect to that measure and so on. But eventually, when I want to deploy a machine learning algorithm, I want some guarantee, right? I don't want to say that, well, according to the existing attacks, I don't identify any risk, but maybe in the future for another type of data, so on and so forth, then there would be a stronger attacker that extracts my data. I don't want that. So what do you want? You want some kind of an upper bound on the potential risk, right? So you just want to say that no matter what the adversary does, whoever the adversary is, the best adversary ever that could be constructed, should not be able to get above this line, right? So the adversary should not be able to increase his true positive rate arbitrarily for any falsehood rate. There must be some bound, right? And that is the so that, for example, the optimal attack is always under the under bound. And this technique is based on the definition of privacy, which is called differential privacy, and the idea is exactly based on the game that we define. So basically what we want is that we want every observation, right, that the adversary makes has more or less the same probability whether he is in world 1 or he is in world 2, right? So he makes a query, gets a prediction. What's the probability of he observing this prediction? Or he looks at the model parameters, what's the probability that he observes this particular value of the model parameters? That should be more or less the same no matter Z is in the training set or Z is not in the training set. If that is the case, then this prevents or mitigates the risk of membership inference attacks and any other attacks. Make sense? Right. But imagine that in the extreme case, if the probability of observing any outcome of this randomized process, because we need to randomize the algorithm to get to this, that's where the probability is defined. If the probability of observing anything, any output, is exactly the same no matter you are in world 1 or world 2, it leaks 0 bits of information about the individual data. Like a constant model which is independent of its training set leaks 0 amount of information about the training set, right? It doesn't matter if Z is there or Z is not there. So there is a trade-off here between the privacy and accuracy of the model, because if you over-randomize it, then what you get is that you get a much tighter bound. The bound gets closer to the x equal to y, FPR equal to TPR, but at the cost of accuracy. But that's a difference. And then here also what we want is that we want this gap to be small. So when I'm computing an upper bound, I don't want the upper bound to be on the edges of this box, right? That's the meaningless upper bound. I want the upper bound to be as close as possible to the optimal attack, which I'm not aware of. So we want the bound to be tight. So any questions so far? After that, I'm going to talk a little bit about how to design those membership inference attacks, because so far I didn't tell you how to do the attack. We talked about why we want to do the attack, what we evaluate of the attacks, and how to interpret it. But how to do it is also fun, and you may want to learn about that. Any questions so far? Yes.
End of the day, I still think that access control is still very important, right? To the model.
Of course.
Because let's say you have a legitimate user, example. Let's say I'm a forensic investigator. I still need to access the model to find out who's the terrorist. Or I'm a business owner. I still want to find out exactly which customer need that particular item that I'm going to send a flyer or whatever to the customer to purchase that particular item. Because both will inflict Personal Protection Act, but both have a case of whether the customer, end of the day, can say, I don't want to receive any flyer, or but for terrorist point of view, the police from the government side, so there's a need to have a various segregation of access rights to do the final protection to prevent unnecessary people to access that whole entire model.
Yeah, of course. Yeah, I mean, this is what I said, right? So you need access control. You need to have mechanism to protect confidentiality of the data. You need authorized access and so on and so forth. You need all that. But there is some type of risk which cannot be prevented by laws. Right? So you have some data here. You make sure that only certain people would have access to the data. You log the access and do all that thing. But you are printing some histograms for your own, other users.
Right.
And the histogram, what I'm saying is that can leak information about the individual data. Right? You print the histogram, you put it in the magazine. Nobody has access to the data. Everybody can see the histogram.
Right.
Right? So what if the histogram can tell that, oh, there exists one guy in the original data set that has this particular property? That's the indirect information leakage, which you did not intend to leak, but the data can leak. And when you go to very high dimensional kind of statistic, machine learning models, they actually memorize a ton of information about the data. They're obscure, you don't see it immediately, but it's there. That's the risk. But obviously, you need to make sure that only limited number of individuals have limited access to the data for specific purposes and so on and so forth. That you should do.
Yes, but why do you want to have that histogram to be exposed in the first place? That's what I'm saying. You access rights to the point of you're not even providing any data to the public.
Computations on the data are provided to the public. That's what I'm saying. Like, somebody trains a language model on thinks that, okay, this language model is going to be helpful for generating sentences, provide access. You have access to ChatGPT now.
Right.
Yeah.
Can I apply, let's say, can I apply things like homomorphic encryption?
No.
Or VVS?
No, because they are protecting as a different threat.
Yeah.
Homomorphic encryption protects confidentiality.
More than that, actually more than that, because if you have homomorphic encryption, fully homomorphic encryption, basically you don't see the data at all. And you do machine learning using fully homomorphic encryption. So you don't see any data, the machine doesn't know what kind of data you're processing.
Yeah, that's
Plus on
confidential.
top of all VBS computation data structure, you actually split out the whole entire data worldwide. You basically don't know which data is which computation is which. So you leak out nothing, whether it is from the data perspective or the computation perspective.
So,
And you only give the final answer to the person who have that particular access rights. So you only let that person that has that thing only. No
yeah,
one
but that
else has-
person, what if that person can reconstruct everybody else's data?
No, it's a segmented process.
It's not segmented. That's what I'm saying. So if two of us want to compute our average salary, let's say we use homomorphic encryption to do that.
Right.
As soon as I know the final answer, I can exactly guess what your salary is.
How? I mean, for 2%, yes.
What I'm saying is that it's an example to make it obvious that the output leaks about the input. And homomorphic encryption, trusted execution environment,
Right.
this, that, multi-party computation, they protect a different threat.
Yeah.
They want to make sure that nobody can see the data and the intermediate steps of the computation. But the outcome is given to someone, and that someone can ask this question. What is the salary of that guy?
If you have if it's only 2%, yes.
If you have n person is also the
Yeah.
case.
Well,
There is information leakage. What is information leakage? What I defined earlier. Before observing the output, right?
right.
Without you being among us. So let's say you are not among us, we compute the average salary. You join, we compute the average salary.
Right.
If the difference is huge, means that your presence leaks information about yourself.
Okay.
The output leaks about the input. That's the
thing.
whole purpose of
That's the
the definition of information leakage, right? So if you are familiar with some other like side channel attacks and so on, is that nobody sees the data, but I measure the temperature of the CPU and I can tell what's going on inside. Right? It's something else that leaks about the secret that you don't have direct access to. So it's very subtle. It's a very good question, but that's exactly where the subtlety of the problem and the difference between the threat models are.
Thank you.
Sure. Any other?
Yeah,
Yes.
actually, my question is related. You mentioned about that you want the predictive probability of some instance to be the same, whether this instance, the game you mentioned about that this
Probability of an output.
yes, to be the same whether this instance in the dataset or not in the dataset. But for some tasks, for example, some instances are critical. For example, if you're doing classification tasks, some instances are pretty critical to determining the decision boundaries. So you actually, if you want the model to be like invariant to this, you will not be achieving like a good performance.
That's true. That's exactly the trade-off, right? So if I would be, let's say, be able to detect, or perform some classification on your data successfully, only if your data is there, it means that this algorithm is leaking a ton of information about your data. So what we need to do is that to suppress that at the cost of having error on some data. So,
Thank you.
but that's exactly the right observation.
Thank you.
Right? So if Bill Gates joins us and then we compute the average salary, it's like whoop. Like, I mean, how do we compute the differentially private average salary? By just suppressing his, by producing something that's as if his data was not among us. Right? The same for machine learning, as you said, for the decision boundary. Any other question? Actually, these are. I can stop here and just continue. Like, I'll give you some ideas about the attack, but this is what is the threat, how to evaluate the threats, and what are the trade-offs. These are very, very important. Any other question? So, how do we formulate the membership inference attacks? Right. So let's say you want to now run a membership inference attack. I give you a model, I give you a data point, and I ask you whether this data point was used for training this model or not. what do you do? What is the simplest perhaps technique that is a decision? It is a decisional problem, right? So you get that Z, you get the model, and you want to tell whether Z was part of the training set of the model.
Do I know the task? The learning task?
Yeah, you have the model. And
Okay.
you know the task, you have all the information.
Okay. Yeah, for one simple thing, if I'm performing well on dataset in sample Z, then the model has most
Awesome.
likely have seen this before.
Yeah, so basically what you're saying is that, well, the error of the model on the data during the, that has seen during the training is much smaller than the error of data it has not seen. And this is some technique that was one of the first kind of techniques that were designed for running membership principle. But let's see how we formalize that. We get to that, and then we'll see what are the shortcomings of this approach, and how we can design stronger attacks. Okay? So the problem is so-called hypothesis testing problem. Hypothesis testing problem says, okay, so at least for this problem that we have, so we have a null hypothesis given Z and a model theta. Null hypothesis is that Z is a non-member, and alternative hypothesis is that is a member. Right? The two worlds. Am I in this world, or am I in the other world? So what we need to do is to simulate the worlds and see what are the probabilities of creating each of these worlds, right? Because if Z is member, it means that, well, some data was sampled for the training, and then a model was trained on it, and Z was actually sampled from the training data, right? Z is a member of the training data. If in the other world where it's a non-member, then data was sampled for training, a model was sampled from the algorithm, and the data point Z was sampled from the population outside this training set. And these are the multiple steps that happen if you want to generate and you want to simulate the worlds. These would help us to construct and reason about the probability of being in each of these worlds. Okay? So then we can, for running the test and that decisional problem, we can use likelihood ratio tests to solve that hypothesis testing problem and say, okay, what is the likelihood of being in world 0, given theta and z that we got, over the likelihood that we are in world h1, given theta and z, right? Then based on this ratio, if this ratio is less than something, then we predict non-member. If it's larger than that, we predict member, and then that's our test, right? So, because one world will be more probable than the other world given z and theta. With some approximations and further formulation of the problem, the attack is basically this. Okay, because I was talking about likelihoods and probabilities and so on. In machine learning algorithm that you train, there's no probability anywhere, right? So, but again, with some approximation, that likelihood ratio test is equivalent to asking the following: if the loss of the model on that data point is less than a particular threshold, then we predict member. Okay, that becomes a test. The question is, what is that threshold? How do I decide which threshold I compare to just say, oh, you're a member or not member? And that threshold depends on many things. It depends on the model, it depends on the data, it depends on the data distribution. It also depends on how much false positive error you would allow the adversary to tolerate, right? If you allow adversary to have a false positive error, 1, then just like this threshold could be infinite, right? Then the adversary would just say everything is member. Right? You want to define this threshold based on outcome. Okay. So how do we interpret this particular test that I just designed? So if we have a loss, now we have you're operating on a one-dimensional space, right? Loss is compared with the threshold. So if you have a loss and a threshold, then basically if on a particular data point is on the left side of the threshold, you just predict member. On the right side, you just predict non-member, right? There are so many non-members, right? So all the data from the population would fall into this category, right? And let's say I just exhaustively go over all the data points which are not in the training set, and I compute the histogram of their loss, which is actually the likelihood ratio under the null hypothesis, right? So for all of these data points on which I compute the histogram, basically I compute the loss, and then none of them are a member of the training set. So I get lots of outsiders, compute the loss, this is the histogram, and you expect your attack to say non-member for all of them, right? But you have a threshold, and for every non-member which is in this histogram that are on the left side of the threshold, actually you are making a mistake. Because these are all non-members, and then they are on the left side, you just say they are member. So this is where your false positive error is. Okay? Given that the loss over the population is this, and a particular threshold, for whatever under this threshold, whatever fraction of the data which are under this threshold, you're making a false positive error, and that region is basically your alpha, right? That is your false positive. Okay, that's the connection between the threshold and the false positive error. Does it all make sense? Right? It was easy because at first I fixed the threshold, and then I just looked at the distribution over the population data, non-members, and I saw which part is making the contributing to the error. I know the alpha. But the challenge is that, well, we don't have that. Like, we have to come up with a threshold. So then you just say, well, I use exactly the same idea that I use for interpretation of this to construct the attack. I just say that, well, first let me just go over a bunch of data points which are in the population and compute the loss distribution of the model on those data points. This I can do, right? And what I would just say is that, well, I look at basically the quantile, alpha quantile of that distribution, because I want to tolerate alpha false positive error, and that will become my threshold. Right? So complete the distribution, see how much you want to tolerate, that region would be your alpha, the quantile associated with that will be your threshold. So now you know that if you say member under this threshold with probability alpha, you are going to make a false positive error, according to the empirical estimation that you make. Clear? Huh? The question would be, oh, how do I compute that threshold? Because when I said loss, I didn't say loss of what on what. I just said on null hypothesis, on non-members, right? So then this would result in some false positive rate with some true positive rate, and then that's your profile. So then the question is how to construct the attack and how to get actually the null hypothesis distribution. We can go back to the idea that was mentioned earlier, and that is, well, the error or the loss of the model on the training data happen to be much smaller on average than the loss and error of the model on the test data. So let me compute the loss distribution under the null hypothesis on the same target model, right? So I get data points from the population, I see how much is the error of the target model that I'm attacking on that data, on those data points, and I expect that the distributions of errors on members and non-members, training data versus test data to be different, and if I compute my threshold based on that, then I'll get a good attack. At least this is a very good attack to start with. Okay? And actually, this is the idea of the first membership inference attack against machine learning algorithm. So basically what I do is that I get data from the population and I get the distribution of that and I compute the threshold. Another thing that I can do is to basically look at the loss of the yeah, this is exactly the same thing that I said. So we have population data, we look at the error that the population, the target model makes on the population data, and then you see on your target data point whether you're, where you are in that history. Okay, so this is the attack. So what are the reasons for leakage in this setting? Right. So basically, if the model is better generalized, then there is less leakage. Right? So if the loss distribution or the population data is more or less the same as the loss distribution or the training data, on this particular membership inference attack, you would not be able to detect members and non-members. So this is kind of a reason for leakage, overfitting. The more overfitted the model is, the more it leaks. Right? That's the idea. So where does this attack make error? Now the attack, the main idea that we came up with is, so let's see, okay, it's cool. If the model is very overfitted, it's going to be very successful. Right? So on all the data points, the loss on the training data is very, very smaller than the loss on any population data, and then I detect all of them. But that's not the case. Models are not that overfitted. And what we look at is this. So if we have these two population data and training data distribution at that particular threshold, we'll see that there are so many data points on the left side in the population data that have small loss. And what are those data points? Those are basically easy data points, right? So the data points on which the model generalizes very well. You are training a model on something to detect flu versus cancer or something. And they're like all these typical flu examples. They could not be they're not in the training set, but the model very accurately predicts the class for them. So these are easy examples. The model makes this membership inference attack that we talked about makes errors on them. Falsely believes that they are member. The model makes also another type of error, which is, again, when you look at the threshold, so there are a bunch of, and then we look at the loss of the model on the training data, there are some on the right side of it where the model makes false negative error, right? So these are the training data points that the model cannot detect as member. Why? Because these are hard data points. Like there is a point which is very hard to find the pattern for it, and even though the model fits on that data, the loss is large. Right? So it's not that when you train a model on a data set, the accuracy of the model on all of them is the same. No, there are some data points that even though the model can make correct prediction, the loss is large. Or maybe the model does not even manage to basically fit that data and the makes huge error because this is a very hard data point. I cannot fit it. Right? So the model makes these errors. How to fix this? By the way, these are the ones that we really care about, right? The data points which are in the training set, the model might make correct predictions on them, but with very high loss, are actually the atypical data points that we care about. We want to protect. Right? These are the ones that leak information. It's a peculiar location trajectory in the data set, or a peculiar disease profile of a patient, and so on. We don't want the model to leak these information, and if our membership inference attack makes error on them, actually we are missing evaluating their privacy risk. Okay? So, what do we do? Instead of looking at the loss distribution of the population data on the target model, we look at the loss distribution of the target data point on some reference models which are not trained on that data point, right? So the question is that what is the output of the model that I'm attacking on Z versus the error of the other models which are not trained on Z, right? So maybe I'm a very hard data point. So if I'm a very hard data point, whether I'm there or I'm not there, the loss value is large, right? But the question is that, so the absolute value of the loss is large, but still maybe when I'm not there, the loss is much larger, right? So I want a more, I want a sharper reference point, right? I don't want to look at the absolute value of the loss. I want to see on the points that models that I'm not member of, how the distribution of my error changes. So now the distribution, the histogram of the loss distribution over the null hypothesis has nothing to do with the population data. It's all about me, my data, Z, on reference models, right? And this gives us a much more concentrated distribution, and then we make less error when we run the attack. So for example here, there's this hard train example, right, that we saw that the previous attack makes errors. Then when you look at the model, the loss of this model loss of this data point on the models that are trained on it versus the models that are not trained on it, we see that they are very distinguishable, right? So this gives a very, very good attack performance. And the reason for leakage is basically what I call the memorization, right? So if I add the data to the training set, how much does the model memorize the data? And this is an example of an easy test example, another type of error that we made. So the data point could be very easy. The loss, absolute value of the loss is very small, but still on models that include me versus the models that don't include me, there's a separation. So I can stop here actually, or maybe like skip some of the more advanced attacks and basically just talk about, like wrap it up here, is that, so all these attacks that we designed, you remember we designed it not to actually attack any machine learning algorithm, we designed them to be able to evaluate and measure the information leakage of models about their data. And this is something that is being used and widely accepted as an auditing technique for privacy risk analysis in at least machine learning. There's a tool called Privacy Meter. It's an open source tool that implements these algorithms. If you are interested in this, you can go and play with the tool. The algorithms are implemented, and it produces all the basically privacy risk reports about which data points are at risk, how much is the false positive versus true positive rate, and so on and so forth. And there are many examples of running this, like we ran it on language models. It tells us how much language models leak information. You ask the language model which data points are more at privacy risk. It identifies the data points. On different examples of language models, like masked language models, which are more complicated, it can evaluate on image classification task. You can run this tool, and you can see that, for example, certain model architecture will leak more information on the same data than others. You can run it on federated learning and so on and so forth. Some very interesting attacks. You can run it against secure multi-party computation that was asked before. If all of us train a model together, somebody want to run an attack and evaluate the privacy risk. So this could be used. The conclusion is this. When we talk about privacy, we need a definition, we need a metric. Privacy otherwise is very vague, like what's privacy? Like you have a different interpretation of privacy, I have a different. We need to have principles on which we agree and say, like, based on those principles, this is my definition and this is my methodology. You can go with another principle, and then for those principles, you have a different way of measuring. If our principle was that what I learn about you when you are added to the data set should not be way different than what I learn about you when you are not there, then this is the definition, this is the kind of metrics that we can use. And for that definition, I showed how to evaluate privacy, what is a privacy risk profile, how the attacks can help to approximate that, how defense algorithms, randomized algorithms can help to bound that leakage, and basically all the challenge if you're doing research is on designing stronger attacks to have more precise lower bounds and more precise upper bound on the defenses. And something that is very fascinating is that, okay, today I just talked about definition of privacy, but there is like so much trade-off between privacy and anything else that you can think about, right? So generalization, then other more advanced topics like fairness in machine learning, robustness in machine learning, model explanation and interpretability in machine learning, scalability of machine learning, and so on and so forth. They're all related to this notion of privacy and memorization that we talked about. Okay, so I'll stop here, but I'll be here for a few minutes if you have more questions. Any questions? Yes, go ahead.
Thank you. Hello, this is Vincent Jiang from NTU. I'm working on the privacy-preserving collaborative learning, machine learning, especially in the IoT. And we are always meeting a problem that we lack of the quantitative privacy analysis or the privacy guarantee. The way we use without the different privacy. So is there any analysis of the privacy guarantee if we use, for example, for the other privacy preserving technique, for the obfuscation, for the data masking, for the random projection? So is there some way or some analysis or tools to give the privacy guarantee if we design a privacy preserving techniques?
If you want to,
without the different privacy.
Yeah, so without differential privacy, you cannot come up with another type of guarantee, right?
Yeah.
On individual privacy, at least based on what we have now, right? The tool set that we have, differential privacy is one way to guarantee that the privacy risk is bounded, right? Individual privacy risk. But if you want to measure privacy, you can use privacy meter.
Okay.
You can use privacy meter and say, like, okay, I have this model, I don't know, compress the model. I don't know, did the dimensionality reduction of data, and then I trained the model on it, or whatever. Before doing that, how much is the privacy risk? After doing that, how much is the privacy risk? It does not guarantee, it's not a guarantee, but it says that based on the auditing tools, we see that there is a improvement in privacy.
Okay, so you mean that without different privacy, you cannot theoretically give a guarantee, but we can measure the privacy loss, for example, from the ROC curve or from the privacy meter?
Yes.
Oh, thank you.
Yeah, thank you for this. I'm also, the idea of using the loss with training data versus the testing data, it's quite interesting, but I believe we can add more level of granularity. For example, using some additional metrics besides the loss, because the loss could be one way of measuring, but it depends in many things about the data distribution itself. Some training data distribution and testing data distribution usually very overlap, and if some data points are outside the distribution, so maybe we can add additional metrics that can be provided with the loss. That if there are cases that the loss is not robust enough to distinguish, we can use some of these metrics. I would think one way that's recently is the uncertainty quantification. So the uncertainty of the model about one data point can be also used besides the loss as a kind of metric.
Yeah. So in general, yes. So as I said, going from the likelihood ratio test to comparing loss with something, right? We need to do some approximations. So loss might not have all the information about membership, but it's the strongest signal that we know now. The error of a model on a data point. Right? So even if I release some statistical model, even if I release some aggregated statistics and so on, always looking at the error is the strongest signal. Right? But you can say, well, what if I have access to because loss is something which you can compute in a black box setting. I just look at the model prediction, I know the loss function, I know the true label, I can compute the loss. If I have access to the model parameters as well, then there could be tons of other signals that you can look at, right? Because loss is just an aggregated metric. So there is a class of attacks called like white box membership inference attacks that they try to look at the model parameters, look at the gradient of the model and data points, a very high dimensional signal, and there you can improve the attack results.
Yeah. Because I believe one limitation of the loss is the availability of the ground truth. For some testing data, you may not be able to have the ground truth, so you will not be able to evaluate the privacy if you don't have the ground truth.
Yeah. So you can like go back to the definition that we had, right? Or the repetitions of the hypothetical experiment that we had in mind. So if you look at the output distribution of a model in one world versus the output distribution of the model in the other world, you can still, do the comparison, right? So, for example, you just know that, on the logistic regression, it gives you a value. I don't know what's the true value, but on the models that this guy was part of the training set, this is the distribution. On the models that this one was not a member of the training set, this is the other distribution, and then you can see how to distinguish them, right? So even though you don't know exactly what the error is. So the output distribution itself can be used, yeah.
Okay. Yeah, thank you.
Very related. But your question fundamentally is the most fundamental question that we're asking, like, what signal to look at, why, what is the optimal, is it one-dimensional, multi-dimensional, should I look inside the model, not inside the model? This is all the question. Because one is the framework, like given the signal, how to run the test, and the other ones are what is the signal? Yeah. It's a very, very important question. Other? All right. Thank you.
Thank you.